Hello, this is Mr. Gilmore with the 9.8 Corollaries and Applications of the FTT. Now, with the FTT, the fundamental tangent theorem is what we just saw in 9.7. That proves that when a line tangent to a circle, a radius is drawn to that point of tangency, that line is tangent to a circle, that the radius and that tangent line are in fact perpendicular to each other. We're going to see that there are some immediate consequences with the fundamental tangent theorem, and we dive right into those with our first proof, called the twin tangent theorem. So whenever you are given a point outside of a circle, from that point, there's actually a construction that is possible with two tangent lines. So our diagram actually gives us this illustration of a point D, external of our circle A, and from that point D, we've constructed two tangent lines, D to B and D to C. Now, what we're going to find then is in our conditional that the tangents from that given point to the given circle are going to be equal in length. Essentially, we're going to prove that DB is equal to DC. And where our proof is, or where the help in our proof is going to come from, it's going to actually come from the FTT, which means the twin tangent theorem is really a corollary of FTT, the fundamental tangent theorem. Let's dive into what the proof of the twin tangent theorem looks like. So here's our proof. We've got our given circle A. We've got these two tangents, DB and DC, which means B and C are the points of tangency. What we're going to prove is that DB is equal to the length of DC. And where we start with our proof is a very simple construction. So we just simply connect A to B, A to C, and A to D. And by this construction there, we've actually formed some of our favorite polygons in the whole wide world, triangles. In fact, we're going to prove that those triangles are in fact congruent to each other. The very first thing we notice is that AB and AC are equal in length. Why? Because they're both radii of the circle. So by definition of radius, we've got ourselves equal lengths already there. Next thing we should notice is that the two triangles share a side, AD. So by reflexivity of quality, we know that that side is equal to itself. That means we already got two things equal to one triangle, or two sides of one triangle equal to two sides of the other. Now we need a third thing. Remember, a magic number for congruence is always always three things. Well, there's one last thing we know. AB and AC are radii drawn to points of tangency, which means by the fundamental tangent theorem, FTT, we can claim angle B and angle C are right angles by the FTT. Now we have our special congruence in this case there because those are now right triangles. We have an equal pair of legs and equal pair of hypotenuses, so we satisfy HL. So the two triangles ABD and ACD are actually congruent by HL, which means our best friend in the whole wide world comes along, says, hey, would you like some equal things? We would. Thank you, CPCDC, which we would like DB and DC to be equal, and that means they are. So the twin tangent theorem, a very nice theorem that actually follows up from the FTT. And actually what's interesting about the twin tangent theorem is it itself has corollaries that immediately follow it. So let's take a look at a corollary of a corollary. If we're given two circles such that the tangent lines are drawn from one circle to the other, from each point of tangency there are two segments formed, AC and BD. We call these the common external tangent segments. What we actually can prove is that these two common external tangent segments are actually congruent to each other. And what we make use of immediately following this is our twin tangent theorem. The twin tangent theorem is the corollary of the FTT, and this theorem, this common external tangent theorem, is actually a corollary of the TTT, the twin tangent theorem, which means this is really a corollary of a corollary. So we're going to prove that AC is equal to BD. Let's take a look at what this proof looks like. So in our proof of AC and BD, we are going to start with a construction. And the way this works is we know that those segments there, AC and BD, are part of lines. In fact, they're part of tangent lines. So let's then extend from those 2 points. Let's continue the line along. So from point A, or our segment CA through point A, we're going to extend our line through point A. And we do the exact same thing with our line segment BD. Let's extend our line through point B. These two segments will in fact intersect. Let's call that intersection point Z. Okay, so in our proof, that's what our construction says. Extend AC through A and BD through B to intersect at point Z. Got it. Now, what we notice is that Z is an external point of both circles. And because of that, not the FTT, that's a typo, we should have the TTT, the twin tangent theorem, steps in and says, hey, you actually have twin tangents. You actually have two pairs of twin tangents. You have these little parts, AZ and BZ. Those are actually a pair of twin tangents, and the whole segments CZ and DZ, those whole segments are themselves equal as well, because CZ and DZ are twin tangents to the larger circle. So if we've got these holes and these equal holes and these equal parts, what we're going to do is we can subtract the parts from the holes, and what we're left with then is the remaining equal parts. So take CZ, the whole thing, and subtract AZ from it. Take DZ, the whole thing, and subtract BZ from it. So by our simple reason of subtraction, we then take these equal things away from equal things, and what we're left with are equal things. So essentially, think about what happens when you take AZ away from CZ. The only thing that remains is then AC. If you take take DZ and take BZ away from DZ, the one thing you're left with then is BD. And so that's really our segment addition postulate, that the sum of the parts equals the whole. So if we take parts away from the whole, we're left with the other parts. And so there we have it, our proof of our common external tangent segment theorem, with it being a corollary of the corollary of really TTT and early FTT. Before we get into our last theorem, though, I do need to give you one quick definition. See, we've seen where a polygon can be created or constructed on the inside of a circle. We call those inscribed polygons, where the sides of the polygon are chords. However, it is now possible with our tangent lines to actually create polygons on the outside of our circle, such that all the sides of the polygon are tangent to the given circle. We call these polygons circumscribed polygons. So in our example below, the quadrilateral BCDE is a circumscribed quadrilateral. Is because all four sides of this quadrilateral are in fact tangent to our given circle A. Now, what's interesting about the circumscribed polygons is there's some interesting things we can actually prove about them, and specifically, we're going to prove something special about a circumscribed quadrilateral. So let me introduce you to the circumscribed quadrilateral theorem. Here's what it says. If a quadrilateral is circumscribed about a circle, then the sum of the opposite sides are equal, meaning pick a pair of sides and pick a pair of opposite sides and add their lengths together. Then pick the remaining pair of opposite sides, add their lengths together. It's what's neat is in the sum of those opposite sides are going to be equal to each other. So in our diagram below, we've got this circumscribed quadrilateral BCDE, and we've got the statement that we're going to prove off to the right, where we're going to prove that BC plus DE is equal to BE plus CD. That's going to be the conclusion of our circumscribed quadrilateral theorem, that we'll actually find that the sum of the opposite sides are in fact equal. So let's dive into what that proof looks like. So again, we're given the exact same diagram. BCDE is a circumscribed quadrilateral about circle A. And what we need to start our proof off with is actually labeling a few points of intersection. Because all four sides of this quadrilateral are tangent, let's label those tangent points and give them names. So I'm going to label these 4 points of tangency right about where we see those lines intersecting our circle at that given point. And let's name this line, these points W, X, Y, Z for each of the 4 segments respectively. Okay. Now, what's happening there is that we now actually have, because of this being circumscribed quadrilateral, we now have 4 points outside of our circle, which means from every single one of those points, there exists 2 tangent lines. And you'll notice that we have those. Focus on point B just for a moment. From point B to point W, and from point B to point Z, those are actually tangent segments from the same point. That should seem familiar to us. It actually goes back a couple slides looking at the twin tangent theorem. And that's where, again, I have another typo there. That should say the twin tangent theorem, because from the twin tangent theorem, we find that from that external point to the both points of the tangency, that the segments produced are equal in measure. So we can claim immediately that BW and BZ are equal in length. And we don't have to stop there, because we have 3 other points that are also external of our circle, which means I can claim CW and CX are equal in length. I can claim DX and DY are equal in length. And I can also claim EY and EZ equal in length. And because of that, we now have all the pieces we need to put the puzzle together to arrive to our conclusion. So if you notice, in our third step, we're claiming all 4 of those twin tangents equal to each other by the TTT. Again, another typo there. I need to fix that. That's the twin tangent theorem. So what are we going to do with all those 4 parts? Well, we're going to be strategic. Let's add the pieces together such that they form the wholes. So for example, BW and CW, if we add those 2 lengths together, we get the whole thing BC. So let's do that in our next step with our simple power of addition. So let's take BZ plus, I did my top segment first. So let's do BZ plus EZ, which we see the parts BZ and EZ add up to the whole segment. We then can take the opposite side, CX and DX pieces, and add those together to equal the whole thing. And what you see there, BZ plus EZ plus CX plus DX, if we add those equals together, then on the right-hand side, we must also add the remaining equal counterparts. So BZ matches up with BW, EY matches up with EZ, CW matches up with CX, and DY matches up with DX. And we add those pieces together. BZ plus EZ gives us BE, CX plus DX gives us CD, BW plus CW gives us BC, and then EY plus DY gives us ED. And thus we have our proof statement. We show that the sum of the opposite sides are actually equal to each other. And again, our recent segmentation postulate, just because we're adding the parts together to equal the whole. And so there we have it, the proof of the circumscribed quadrilateral theorem. To end our lesson today, let's just take a look at a couple examples of what you're going to experience on your homework assignment. This first example actually goes back to the 9.7 lesson, because really what the homework example is going to be, it's going to be a molding of the 9.7 lesson and the 9.8 lesson, because we've seen that in 9.7, the fundamental tangent theorem and the importance of that evolved into these three theorems today. And so they're all tied together because of that fundamental tangent theorem. So this example in our first slide here for examples is one using the FTT to justify what we know and what we're going to use to prove or to find this missing segment AB. See, we're given this diagram below where we may assume that segments which appear tangent are tangent, which means the segment BC, it appears tangent to my circle. Then we can safely say it is a tangent to our circle there. And we also have our segment AC, that radius drawn to the point of tangency. Because of that, we know something special about that triangle ABC. We know this triangle then to be a right triangle because of the FTT. So the FTT is a reason that we'll actually see on our homework assignment tonight. Again, 9.8. So we now know that it's a right triangle. And you'll see that above, I give you two sides of that right triangle, which means you can find the missing third side, AB, by using the Pythagorean theorem. A squared plus B squared is equal to C squared. So fill in what we know. We know A squared. We know our B squared. We're looking for our C squared. So 3 squared is 9. 9 squared is 81. And let's add those together. We get C squared is equal to 90. And then we take the square root of both sides and we get C is the square root of 90. However, 90 does have a perfect square factor on the inside of it. It is square root of 9 times 10, which then means the square root of 9 gives us a 3. Square root of 10 gets stuck on the inside, and there we have it. We have our answer for our missing side measure. Our side AB is 3 root 10. All thanks again to the fundamental tangent theorem to help show that that actually is a right angle, which gives us a right triangle, and with right triangles, we can work with the Pythagorean theorem. Our last example is going to be using this circumscribed quadrilateral. However, what's interesting about the circumscribed quadrilateral is it's actually easier for us to use not the circumscribed quadrilateral theorem, but the theorem that actually supports it, which happens to be the twin tangent theorem. Because in our given information, we're going to be given information about the tangent segments, and from that, using the twin tangent theorem, we're going to be able to figure out what these missing segment measures are. So again, we're allowed to safely assume that segments appear tangent. They are, which means we do have a circumscribed quadrilateral. Points I, F, G, and H are tangent to our given circle. And we're given some information about some of those segments that we're going to use then to find our missing segment BC. So we're given that BI is 6. We're given that both EH and HD are 4. And we're given that this little segment CG here is 2. Our goal is to figure out what the entire length of BC is and the entire length of CD. Let's start then by using what we know about the given segments. So the given segment BI, consider the point B. It's external of our circle, which means BI and BF have some relation to each other. They are twin tangents. That means they're equal to each other. So that means BF is also a length of 6. EH and EI, same story. Those are twin tangents, which means they're both a length of 4. HD and GD are also both a length of 4 because those are twin tangents. And then we have CG and CF, which is also a pair of twin tangents. So they must be equal in length. And that is all we need to know now to figure out what our missing segment measures are. BC, as you see, then our two subparts are BF and CF, which is a length of 6 and a length of 2. So we add those lengths together, we get a length of 8 for BC. And CD also has two subsegments, CG and GD, which is a length of 2 and 4. So we put those together, and we end up then with the total being 6. We find the missing length of CD as well. So there we have it. We're using our twin tangent theorem in this case to actually help us find those missing segment measures. You're going to see some similar cases just like this on your homework assignment tonight. So please be sure to hop over to look at the 9.8 assignment, where you are going to be given space for you to recreate those three theorems that we saw in this chapter, in this last lesson. And also you're going to have a section on application using those three theorems in addition with the fundamental tangent theorem itself. So if you are working on that homework assignment and you do come across any questions that you need help on, please do not hesitate to email me. I will get back to you. With that, be good and do good.